Welcome to the fifth and final video meant to accompany the stress combination example problem. In this one, we will sum up all of the stresses that we've found, and we will use Mohr's circle to determine our principal stresses and our maximum in-plane shear stress for the plane of for the XY plane. Should be a good time. Now that we've determined the stress from all of those sources, we'll need to sum them all together to obtain our stress state at point H. Remember, this is only hold for point H. So, our normal stress in the y direction is going to be equal to negative 0.0110 megapascals. That's from the axial load, from that 20 kilonewton load produced downward. And then we're going to have it be minus 0.0975 megapascals. That's from the bending moment in the about the x-axis. And then we're going to have plus 0.3 megapascals. That's from the longitudinal stress from the pressure. So summing all those together, we're going to get 0.2014 megapascals. Our stress in the x direction, we've only got one source for that. That's the hoop stress from the pressure, and that's going to be 0.6 megapascals. And then for our shear, I called it in the y-x direction. It's the same as the xy direction. We're going to have shear from the lateral shear of 0.0110 megapascals. Again, same as up there. And then we're also going to have 0.02437. And we said those were in the same direction. And that ends up being 0.03539. I guess I should have written 4 megapascals. So that's going to mean that our stress state that we're starting from is going to look like this. Right? Let's just, doesn't have to be huge. But let's draw out the state that we're working with here before we get to drawing it in Mohr's circle. Okay. So this point at least has the advantage of being in the x and y direction, so we can draw it in our most conventional way. Right? This is going to be the y direction. We got 0.2014. And then we're going to have 0.6 in that direction, in the x direction. And then we're going to have shear. Oh, I shouldn't have written that there, huh? And that's going to be 0.3, 0.3539 megapascals, and that's also megapascals, and that's also megapascals. Okay, so this is the state we're working from. Let's use Mohr's circle to rotate this about. Now there's a circle. Let's use it to determine our maximum in-plane shear stress and our maximum, our principal stresses. Alright, so we're going to start from, well, let's draw the axes in. I traced a circle using a glass. I didn't put the axes on. Here's our normal stress axis. Normal stress. Here's our shear stress axis. I'm going to draw it out over here. I don't want to deal with more lines in here than I really need to. Our shear stress. So we're going to start with 2 points. I guess one of them right here and one of them right here. I drew the circle before drawing the points. Obviously it's not how you do it in theory, but it's how you get a nice circle. This first point is going to be 0.2014 megapascals, 0.03539 megapascals. At that point, this one right here, it's going to be 0.6 megapascals. That's easy. And then negative 0.03539. And then we can just go ahead and connect them. And I guess our starting points are in red. Okay. Alright. It wasn't perfect. That's not the center. But we can right away say, and I'm just going to go ahead and do this over here, that the average normal stress, well, that's going to be 0.6 megapascals plus 0.2014 megapascals over 2. You know how to average things. And that's going to give us 0.4 basically. But, you know, with a little bit of change from that, 0.007 megapascals. Looks like I forgot the A there. There we go. So that's that point right there, which I realize is not in the center of the circle. What can you do? I don't think I drew this exactly in the middle anyway. So now we've got that average. Let's take one of these triangles out. I'm going to pick this one this time. On account of how it's right there. And so I'm going to look at this triangle we've got right there. And I'm going to say that the radius, which is going to be this distance, is going to be equal to the square root of the sum of squares of this distance and this distance. And this distance is going to be what did I say this was just now? 0.407. Oh, there's 2 zeros in there. Megapascals minus 0.2014. That's that distance right there. Square it. Well, this is going to be a lot longer. Plus this distance. Well, this distance is a lot easier to determine, right? It's going to be 0.03539 megapascals. Square that. And that's going to give us a radius of 0.2024 megapascals. And that's also going to be our maximum shear. So I'll do that in red. Yes, red. Our maximum in-plane shear is going to be 0.2024 kilonewtons per millimeter squared. And of course our principal stresses will be pretty easy to find. Our principal stresses are going to be equal to the average plus or minus the radius. And so that's going to equal, well, let's go ahead and cut to the chase, right? It's 0.4 plus or minus 0.2. So it's going to be just a scotch more than 0.6 and just a scotch less than 0.2. It ends up being 0.6031 and 0.1983. So those are our principal stresses for point H, and this is our shear stress for point H. So there's quite a bit to get to our principal stresses at that point, but there was a lot going on in this problem. We had 2 forces with quite a distance. So we're going to have, we have moment from both of them, and we have torsion from one of them, and we have shear from one of them, and then we had the pressure vessel thing, which is a whole nother thing. This has just a lot going on as far as combinations of stresses go. Obviously, when you look at this problem, it's probably not H that's going to be experiencing the most. Well, it might not be H that's experiencing the most, right? Because we had nothing from the bending moment right here caused by about the x-axis. So we'd also want to consider each of those points, not just H, but also I, J, and K. So you might want to do that on your own. Might be a good thing to do. All right, stay safe and healthy.